Continuation with the equivalent circuit diagram of a transformer. In this particular session, we'll see that how to draw the vector diagram and do the calculations for simplified equivalent circuit diagram referred to the primary side. We will recall once again the equivalent circuit diagram transformer referred to the primary side. We know already that is R1 and X1 are the resistance of the primary, R2, X2 are the resistance and reactance of the secondary. Then when if you are referred to the primary, R2 and X2 are brought to the primary side. Then you are drawing the equivalent circuit diagram. You can see R1 and X1 we are keeping intact in the primary side. R2 and X2 are transferred from secondary to primary with its equivalent resistance of R2 by K square and X2 by K square when if you are transferring from the secondary to the primary. Similarly, this voltage V2 also transferred to the primary side with the V2 by K. Then we are introducing here, this is the no load component with the R0 and X0, R0 and X0, and R1 and X1 as nothing but the resistance and reactance of the primary, and similarly R2 and X2 which is in the secondary, that already transferred to the primary side. This is the equivalent circuit diagram of the transformer referred to a primary. Still I am doing the simplification of this particular diagram by just I am assuming that the current which is drawn here I0 is very small. Then if you are transferring this particular the parallel to element to the initial portion of the circuit, still the circuit is simplified with a small error, because I0 is very small. It does not affect if you are shifting this to the input side here, that is towards the V1. That is why what I am doing here is I am shifting this two elements at the beginning of the circuit to make the circuit still simpler. Okay. Therefore, what I am doing here is I am shifted this parallel combination, instead of here I am putting here, means the current here is drawn is I1, but current drawn here is I0, because we know that the total I1 is the vector sum of I1 dash and I0. Out of I1, if the I0 is drawn here, now the current which is flowing here is I1 dash. Just due to what is small, there is a change between these two circuits you can observe here. Previously, the current which is flowing in R1 and X1 is I1. Now it is R1 and X1 is I1 dash, because we are changing these two elements at the beginning of the circuit. But the current I0 is very small, therefore it does not affect the overall the circuit of the transformer. Therefore, now with the changing scenario, by shifting this element, the current here is I1, here it is I1 dash, but here it is I1 dash only, it is I1 dash here, it is the same I1 dash is flowing here, I1 dash here. By shifting this element from here to here, the advantage is that you can add these resistances and the reactances. That we will see here in the next slide. You can see here. Here I am drawing the same figure here once again. It is R1 and X1, R2 by K square, X2 by K square. Now what I am doing? I am adding the two resistances, I am adding the two reactances. I will draw one more diagram. The same parallel element. Now instead of the two resistance, I am simplifying adding these two. Therefore, that resistance what I am calling is RO1. The RO1 is the sum of these two current, then it is called as equivalent resistance referred to the primary side. That is R1 plus R2 by K square. Similarly, X1 and X2 by K square are combined and it is XO1 is the reactance referred to the primary. That is the total equivalent reactance of the transformer referred to the primary side. Then circuit is very simple. Previously we have got to the 4 element 1, 2, 3, 4. That is what you are seeing in the slide. It is R1, X1, R2, X2. There are 4 elements, 2 resistance, 2 reactance. Now the circuit is reducing to 1 resistance and 1 reactance. And the calculations are nowadays very simple. Calculations are the simple. Okay, that is same V1 and V2 by K is here. It is I1 dash and V2 by K. Now I am doing further assumption. That is why I am putting here it is an approximate equivalent circuit now. What I am drawing here in approximate equivalent circuit. That is making the circuit as simple as possible for the calculation purpose with sacrificing little bit of accuracy. Means here we are shifted from this point to this point. This is one assumption we are made. For drawing the approximate circuit, then what I am doing here is this element is very small because I0 is very small. Then it's totally neglected. Therefore, what I am writing is this is circuit. What I am writing is RO1 and XO1. That is RO1 and XO1. Now, if you are removing this particular element, then the current which is flowing in the R1 and X1 is I1. That what I am showing here. Means the input voltage is V1 and the voltage across the load is V2 by K. Same thing I keep it. I am go on reducing the circuit step by step so that make the calculations very simple. Therefore, what I am getting is RO1 here and XO1 here. Now, with the help of this particular diagram, then you have to draw the vector diagram. That is the voltage equation of a transformer for a approximate equivalent circuit diagram. Whatever I shown this particular diagram, I want to draw the vector diagram and I am establishing the relation between V2 by K and the V1. That is this voltage at the load voltage to the supply voltage. Okay. Now once again I am drawing here the diagram. Then here what is the starting point? That is we know the condition at the load end. From the load end you have to go towards the supply end. Okay. What is the voltage here? V2 by K. That you take as a reference. What is the current here? The current which is in the circuit is it is referred to the primary side. It is I1. Therefore take the V2 by K as a reference. Then for example now I am taking for a lagging power factor. The current I1 lags V2 by K by an angle of 5 because I am taking here lagging load 5. Then to this V2K, how to get V1? How to get V1 from V2 by K? You have to add the drop across RO1 and add the drop across XO1 so that what I am getting is V1. To V2 by K, first what I am adding is I1 RO1 drop where I have to add to the V2K. That is I have to add I1 RO1 to the tip of this. That should be parallel to I1. Because I1 R1 here, what I want I1 R1 to the tip of V2 from here to here I am shifting. Therefore, I am drawing I1 R1 which is parallel to this. Then the next voltage of what I am adding here is I1 XO1. I have to add. Then what should be the phasor of I1 XO1? I1 XO1 should be the perpendicular to the current I1 or it is a perpendicular to I1 R1 because already it is drawn parallel to this. Therefore, draw I1 XO1 the perpendicular to this. Therefore, what I am getting is I1 XO1. Then sum of V2 by K plus I1 R1 plus I1 XO1. Then what I am getting here is the applied voltage V1. Therefore, if you are adding these two from here to here, that is what I am getting is I1 Z1, that is impedance drop, because R1 plus JX1 into I1 is nothing but impedance drop. This is the way to draw the vector diagram for approximate equivalent circuit. Okay, it is in the form of V1. How we are getting V1 vectorially? By V2 by K, V2 by K, you have to add I1 R1 plus JX1, that is impedance drop. Or is in the split it is I1 R1 plus I1 X1, it is a vector tensor. Therefore, instead of separating R1, R01 and X1, I am putting in the form of impedance form, that is R1 plus JX1, that is nothing but V2 by K as it is, V2 by K plus I1 Z1. Okay. Now, we have to see this vector diagram or the equation for this V1 for different types of load. The first for lagging power factor. For if the load is for lagging power factor, so what is the V2 by K? V2 by K is taken as a reference. Therefore, I am writing this as a V2 by K an angle of 0 degree. You need not bother about the complexity. If you are putting in this particular form, it is very easy for your calculation purpose. That is why I am making this particular slide here. That is, this is a basic equation. The V2 by K is nothing but, because you are taking this as a reference, therefore you are taking V2 by K an angle of 0 degree. Then, for it is a lagging power factor, the current I1 lags V2 by K an angle of 5. Therefore, instead of writing I1, I write in the phasor form. I1 is I1 an angle of minus 5. Why I am taking minus 5 here? Because it is a lagging load. In this equation, if you are putting this, then the calculation is very simple. Therefore, V1 is equal to V2 by K an angle of 0 degree, I1 an angle of minus 5 R over plus JX1. Just if you have got a numerical values of all these values, directly you have to substitute here, and if you are making the calculator, you are getting directly the answer for V1, because V2 by K magnitude is known, phase angle is known, this phase angle is also known, magnitude of I1 is known, R1 and X1 already you are calculated. Similarly, for leading power factor. Once again, what is the voltage? Voltage is a reference. Therefore, V2 by K is V2 by K an angle of 0 degree. Now, the current I1 is here. In the case of lag, it is minus 5. Now, we have to make use of plus 5. That's all. I1 is equal to I1 an angle of 5. Then, how to write this equation? That is same thing. That is V2 by K an angle of 0 is a reference. Here, while writing I1, what I am writing is I1 an angle of 5, because it is for leading power factor, angle is plus. Therefore, 5 into bracket R1 plus JX1. If the power factor is unity, in that case, if the power factor is unity, once again V2 by K is a reference. It is a V2 by K an angle of 0 degree, and I1 is equal to, now the power factor angle is 0. That is, it is unity power factor. Therefore, phi is 0. Therefore, straight away I1 is equal to I1 an angle of 0 degree. Therefore, the equation is V2 by K an angle of 0 plus I1 an angle of 0 R1 plus JX1. This is how we have to write the equation in the polar form and the combination of R1 and JX1. Suppose if you want do the calculation the mathematically, then you have to go for this particular the diagram once again. It is for lagging power factor. I will show you, and later on how to calculate for leading and lagging I will explain. First, once again the same thing. V2 by K is a reference. Then I have got current I1 lags, V2 by K angle of 5. Then I1 R01 is drawn parallel to the I1 because it is a resistive drop. Now I am resolving this into two components. And there is a I1 X01, then it is a total value of V1. Okay, therefore it is I1 Z01, what you are getting. Now, Step by step I want to resolve so that I have to get mathematically V1. Okay, just you can observe here. I draw once again V2 by K as the same diagram. Then drawing the I1 RO1 which is parallel to the I1. Then what I am doing is I am extending this and I am resolving this I1 RO1 along its X component and Y component. Okay. That is, once again this angle is phi because it is making an angle of phi. If you are drawing here a line and if you are measuring this angle, this is also angle phi. Now I am representing the different vectors, that is it is AB, it is a BC, that in BC I am resolving into two components. That is one is DC, there is another one is BD. Then if you are looking into this particular triangle, then you can find out what is the value of DC and BD. Just I am making here. That is in triangle BCD. If you are taking cos phi is adjacent side divided by hypotenuse. That is BD by BC. Then what I want is BD. Therefore, it is BD is equal to BC cos phi. It is a BC cos phi. BC is nothing but I1 R over 1. Then that is nothing but I1 R over cos phi. That is, I got this particular component. That is X component of I1 R1. Similarly, you have to find out DC by applying the sine function for this particular triangle. Therefore, I am applying sine function. It is opposite side divided by hypotenuse. That is DC by BC. Then the DC is BC sin phi. That is equal to I1 R1 sin phi. Means I am getting this. Okay. Further I am proceeding. That is I am drawing I1 R1. I1 R1. Once again I am resolving this I1 R1 along its X and Y component. Okay, this is the X component of, Y component of this vector, and it is a Y component. It is a X component. It is a Y component. This is X component. This angle is phi. You can see here. This is phi. This is phi. This is 90. It is 90 minus phi. It is also 90 minus phi. It is 90, and ultimately this is phi. This angle is phi. Means if we are taking into this as a point F and this as a G, then for this particular triangle, once again you have to apply cos function and sine function. What I am getting is in CGF, what I am getting here is cos phi. You can apply cos phi. Cos phi is adjacent side divided by hypotenuse. That is FG by CF. Therefore, what I am getting is FG is equal to CF cos phi. Similarly, I want CG, then I am applying the sine function. That is sin phi is equal to CG divided by CF. CG is equal to CF sin phi, and CF is nothing but I1 X1 sin phi. Means what I am doing here is I am resolving this I1 R1 and I0 X1 to its X component and Y component, its X component and Y component, so that I want this resultant voltage V. Just how we are getting that, we will see that. Then I am making some, I am extending this to here, it is becomes a T and it is H. Okay, I am extending this to up to this H, this I am extending to D. Okay, now I have got a same V, the same vector diagram drawn, only I am resolving I1 R1 and I1 X1 into its X and Y component. Now what I want is this AF. What I want is AF. That is nothing but our voltage V1 I want. That is, if you are looking into this is a right angle triangle. This is a right angle triangle. In this right angle triangle, that is V1 square is equal to AB plus BD plus DH whole square plus FH whole square gives the V1. Just I will write here for representing this. That is for lagging power factor load. I am taking the in triangle A